Oh, okay. Hi, everybody. So I'm going to present all of Chapter 7 in this presentation, in this slideshow. I usually break it up, but we don't have time. And it's information that you know from me or from chemistry, honors chemistry last year, AP Chem now. So it's a good review for those that are doing their AP Chem or even honors chemistry at this point. So here we go. Using the spectrophotometer to detect molecules, Chapter 7.1. Okay, so I'll go over describing how a spectrophotometer operates, compare and contrast ultraviolet and visible white light spectrophotometers, and give an example of their uses. We'll look at which type of spectrophotometer is needed for a particular application and the wavelength to be used. We'll look at the relationship between absorbance and transmittance in spectrophotometry and interpret the meaning of absorbance measurements. And we'll look at Beer's law or Beer-Lambert law. We don't usually have been talking about that in biotech, so this will be our way to go over that, and then it may relate then to chemistry. Explain the relationship of absorbance and concentration of molecules in a solution, and define and describe absorbance spectrum, and of course define and describe lambda max. Okay, so finding out what molecule you have is important for research and development. The quickest way is to put an indicator in it. It's a solution. You put an indicator in it. Bradford Biuret reagents, we've worked with those. Turn color in the presence of a protein. DPA and ethanium bromide will be turning color in the presence of nucleic acids, DNA and RNA. And we use methylene blue for loading dye and for staining. Iodine turns color in the presence of starch. We know that about that when we did the amylase assays. And Benedict's glucose test strips will change color in the presence of monosaccharides. Again, we used those in our amylase assays last chapter. Okay, a spectrophotometer is a common way to detect and measure the amount of molecules in solution, using some type of light to detect molecules in solution. So light is reported in wavelengths, and that's nanometers. And we have two types of specs that we have in our lab. And of course, you've been using just the visible spec, the VIS spec. That's using visible light in the range of 350 nanometers to 700 nanometers in electromagnetic spectrum. The UV spec would be using ultraviolet light at the 200 nanometer to 350 nanometer range. And that's for things that you are basically not adding indicators for. They would be colorless. Okay, so here's absorbance, transmittance, and reflection just through a little cuvette here of something that has been a colored solution that's been dyed with some kind of indicator. Okay, so a spectrophotometer will measure how light interacts with atoms or molecules in a sample. So you have some wavelengths, of course, light will be transmitted between atoms and molecules and pass through the sample. So that's transmittance. And then some wavelengths of light will be reflected off the molecules and bounce out. And then some wavelengths of light will be absorbed by the molecules in the form of exciting electrons to higher energy levels. And here goes a UV spec, how it works. Similar to a VIS spectrophotometer, the UV spec shines ultraviolet light or visible light on a sample, and detector measures the amount of light that passes through it or is absorbed by the sample. And there's our colors of light in the visible spectrum, the electromagnetic spectrum. Humans can only see light with wavelengths of about 350 to 700 nanometers. Okay, UV, FIS, and UV spectrophotometers. UV detects colorless molecules this is where you get a little bit of a blip, a change in the book versus what you might see here. We'll go to 200 to 350 nanometers. Sometimes some UV specs will go as low as 100 nanometers. The visible spec will detect colorful molecules at 350 to 700 nanometers. Okay, electromagnetic spectrum, just kind of an overview of what, if you're not remembering about a wavelength and then frequency and light and how it travels, what have you. Let's go over that a little bit. So all types of light all types of light energy travel through space in waves. Light waves come in different forms and colors, including blue light, violet light, UV light, red light, and infrared light. What we see is the narrow range of wavelengths called the visible light spectrum. So the relationship of wavelength, frequency, and energy. Light that has shorter wavelengths will have higher frequencies and more energy. Light that has longer wavelengths have lower frequencies and less energy. And we all know the little Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. We looked up at a rainbow. And we have the red end is about 700 nanometers. Okay, these are longer wavelengths. They have lower frequencies and less energy. The infrared, the red, the orange, the yellow, the green, the blue, the indigo, and the violet. Then you get to 350 nanometers. It's the distance between peaks of a wavelength. Then you're getting into higher frequencies, how many waves pass through per second, and then you get more energy. So you're in the ultraviolet. Then you move into those higher or more energy forms of light. Okay, why do some substances appear colored? So when this light passes through a substance, certain energies or colors of the light are absorbed, while other colors are allowed to pass through or are reflected by the substance. So if a substance doesn't absorb any light, of course, it appears white, because that's all the light. All of the light is being reflected back into our eyes, and or colorless, and that's all light would be transmitted. A solution appears a certain color due to the absorbance and transmittance of visible light. So, for example, a blue solution appears blue because it's absorbing all the colors except blue. We see blue. So here comes a color wheel, and this is really handy when you need to know certain things about what you're working with in a spec. I think we've done this before. We've talked about this before, and probably Miss Lehner has in the past. But what you see here is that a sample may also appear blue if all colors of light except yellow are transmitted. Now, this is because blue and yellow are considered complementary colors. As you can see, if you go from blue there, over on the other side of the wheel is yellow. Okay, so if you want to know what colors are absorbed by a pigment color and its wavelength range, just check the complementary color chart. So if you look at blue, I see blue, and it's absorbing between 560 and 580 nanometers, so in the yellow range. So that's what's being absorbed by that blue. We're seeing it as blue, but it's absorbing the most between 560 and 580. If I see something that's red, it's absorbing in the 490 to 560 nanometer range. That's the maximum absorbance of the color that's being absorbed for me to see red. Red is being seen because it's reflected out. All the other colors are really being absorbed, but the most absorbance is happening in the 490 to 560 because that's the complementary color of red. So red is the color I see, green is the complementary color, and this is the maximum absorbance, the wavelengths that are being absorbed by that solution, that red solution. If it's a blue solution, it's around in here. If it's a violet solution, this is what's being absorbed. And if it's orange, this is what's being absorbed. If it's yellow, this is what's being absorbed. Violet, if it's green, this is what's being absorbed. So that's the gist of it. Okay, so if transmitted color or complementary color in nanometers and absorbance. So if red is what you're seeing at 630 to 750 nanometers, it's green that's being absorbed the most, and that's in the actual being absorbed in the actual solution at 490 to 530 nanometers. If you see yellow, then your absorbance is in the 400 to 420 range, the violet. If you see blue, it's orange. It's what's being mostly absorbed at the 580 to 620 nanometer. And later on, we'll talk about that's where the lambda max is, where you'll find it there. Okay, so how a spec works, the basic operation of a spectrophotometer includes a white light radiation source that passes through a monochromator or that monochromator. A monochromator is either a prism or a diffraction grating that separates the white light into all colors of the visible spectrum. There's a cute little science fair experiment in Science Buddies where you can create this kind of thing along with a program you use on your phone where you can take, like I have diffraction grating I bought, and you can just put that together with a light and get the whole thing going on a board. But that's the gist of it. Here's the light. Here's the prism of diffraction grating. It's going to go through. Then it's going to pass through a filter, and that's going to block any unwanted light, sometimes light of a different color. And then there's a slit to narrow the beam of light, making it form a rectangle. Next, the beam of light passes through the sample that's in the sample holder. The light passes through the sample, and unabsorbed portion strikes the photodetector that produces an electrical signal, which is proportional to the intensity of the light. That's photons per second, the intensity. So the signal is then converted to a readable output that is used in the analysis of the sample. So the big thing I want you to get out of it is that detector is detecting transmittance. So your spec initially is detecting transmittance, how much light has passed through the sample. Then you change the mode to absorbance when we do calculations, when we want to know concentration of the solution. So it's first getting, the detector is picking up transmittance. Okay, so the light that passes through the sample is either then absorbed by the molecules, reflected off the molecules, or transmitted through the molecules. Here comes some values here. Transmittance is usually in percent, T, percent transmittance. So it's from 0 to 100%. And that's the percent of light transmitted. And absorbance is the amount of light absorbed by a sample. So in our old-fashioned, the ones we had in the classroom there, the old specs, we could only go up to 0, up to 2. It was 0 to 2. And there's no real unit. It's just like you would make it AU, or there would be no unit. It's just absorbance. Usually you put AU as its thing. Of course, the ones that I've been having you use a lot this year, we're going up to 3, which was really handy. And that's better if you have certain things you're working on. Okay, so then the amount of light absorbed by a solution is dependent on the ability of a compound to absorb light, and that's called molar absorptivity. The distance through which the light must pass through the sample, that's the path length, and the molar concentration of the compound in the solution. So if the same compound is being used and the path length is kept constant, then absorbance is directly proportional to the concentration in the sample. So this is something that really helps us out with all the things we do, right? So if we have the solution and we get its absorbance in the spec, then we can know that the higher the absorbance, the higher the concentration. Obviously, that's intuitive because it's a darker solution, so it must be picking up more light than it would if it was a lighter solution. So that's great to know there. So that comes along, and that's this whole equation called Beer-Lambert or Beer's law, and it puts together Beer-Lambert law, sorry. It's transmittance, absorbance, and the Beer-Lambert law. So we define transmittance as the ratio of the amount of light transmitted to the amount of light that initially fell on the surface. So let's imagine this is the cuvette inside the spec, okay, and it has a sample, and it's a colored solution. Now, I0 is the incident light beam. It's in photons per second, and of course it's coming through, and it's coming from the light source, and then there's the prism or the diffraction grating, and now it's slit, and all of that's here, and then it goes through, and then it hits this cuvette with the solution inside. This little L here is the length of the light path, and it's usually fixed, of course, because it's just the cuvette, whatever, 1 centimeter usually, right? That's it. And then this I alone, intensity, is the transmitted light beam. So it's all intensity. This is incident light beam. This amount of photons per second going through, starting to get, it goes to the cuvette incident. Then there's a relationship of that photons per second over that intensity I. It's the transmitted light beam that's coming out of the cuvette. Okay, and that's, again, photons per second. Okay, then there's absorbance is defined as the negative logarithm of the transmittance. And you will note that absorbance and transmittance will bear an inverse relationship. And that, again, makes sense intuitively, right? They're inversely related to each other. So as you decrease the percent of transmittance, there's an increase in absorbance, right? Because there's not as much light passing through, it's being absorbed, and vice versa. So we set it up as absorbance equals 2.00 minus log, and then you have percent transmittance in parentheses. Now, A is absorbance, percent T is percent transmittance, which can also be noted as intensity over intensity ought, or I ought, because again, you're thinking, okay, this is the ratio of the photons per second that are passed through the cuvette over the photons per second that actually we're going to go into the cuvette times 100 to get the percent. Then you can extrapolate 2, minus log T times 100 equals 2 minus 2 log T equals negative log T equals, then you have an equation that's workable, which is absorbance equals negative log I, or intensity, over I ought. And if you want to turn into percent, you would just change that to, times 100 to get percent. And it gives you a way to look at absorbance being inversely related to transmittance. Okay, then there's absorbance and concentration of molecules in a sample. As we said, absorbance and concentration are directly related to each other. They have a direct linear relationship. So the more molecules you have in solution, the higher the light absorbance is for the sample. So if there were twice as many molecules in solution, then there would be twice as many light would be absorbed. Likewise, half as many molecules absorbed half as much light. And this is a good little thing for you to see. And we've done this. You've done this since Biotech 1, whether you knew you were doing that or not. The concentration versus absorbance. And you had your standards. And, we've done that quite a bit too. So, okay, then Beer's law is absorbance and length of light path. So as the length of the light path increases, then the absorbance would increase, that would make sense too. As you got this larger and larger, then there'd be more light being absorbed by the sample. So, but we never really changed that. I mean, if you have a different kind of spec, maybe there would be a difference, but it's usually the same for machines that you're working on in the lab, and that stays fixed. Okay, so explain the relationship between absorbance and transmittance, and you could utilize this equation. And I actually have this in your notes there. You'll see some things you can use, but you will need your calculator to have the log functions on it. And I think by now everybody has that. Or you could use calculators that are online. There's some calculators online you could use. So you can get your absorbance value by just getting your intensity over intensity ought. You get those values. There are photons per second. You get those values. You plug those in here, and then you do the negative log of the absorbed. You get that, and you get your calculation answered there. Explain the relationship between molar absorptivity, light path, and concentration. Again, these are all Beer's law, Beer-Lambert law as a summary here. There's absorbance. This little epsilon is indicating molar absorptivity. The lowercase l is your length of your light path. And then little c, of course, is solution concentration. Let's just say it's in molarity. It's moles per liter. So it's molarity there. Now, because molar absorptivity, this is all like with units, and that would work out. You just keep the concentration at moles per liter. So molar absorptivity is interesting because it is a constant, and you can look it up for properties. It gives you, it's like it's constant dependent on actual properties of the molecule itself that's in the solution. And many years people have been putting together this lab that I guess for the last year or two we haven't done it, but it was cute. It was about sunblock and SPF and how you can take an ingredient that's in sunblock and you can see the activity or effectiveness of different sunblocks using a UV spec, but you would do like standards, and it's hard because it's opaque, the sunblock. So you have to really get it in a very, oh my gosh, your dilution has to be like, I remember people fiddling with this, like 1 to 500, really, really dilute solution of your sunblock. And then you use the UV spec and you get values and you can figure out the molar absorptivity of certain sunblocks. And there's a relationship of that molar absorptivity to its effectiveness, to how well it works. And it's a good kind of consumer kind of thing. So I know you're just kind of doing a makeshift science fair project now because of our situation, but if next fall you say, hey, I'd like to do something with sunblock and use a UV spec, you'll be using it next year anyway, so the UV spec. So it's a pretty good little experiment. It was cute. People have done that, and it's a cute little thing. Okay, so just definitions for chapter 7.1. Absorbance spectrum, it's a graph of samples absorbance at different wavelengths. It's like the molecules absorbance fingerprint, and you're comparing wavelength to absorbance. Now, lambda max is a wavelength. It's not anything else but the wavelength, since lambda is the actual symbol for wavelength. So a lambda max is a wavelength, that peak light absorbance. So the lambda max for a molecule is the wavelength that should always be used to study the molecule, since at lambda max, the molecules are most strongly detected. So when we go back to this, let's go back to the color wheel. So if we go back to the color wheel with this, you can predict your lambda max. If you have a red solution, your lambda max is supposed to be around in here from 490 to 560 because of peak absorbance. Remember we said the complementary color is about where the peak absorbance is. If you have a yellow solution, you can predict that the lambda max could be somewhere around here, 450 to 400 to 450. Then if it's a blue solution, it's in this range, the orange, 580 to 620. So that's where you find your lambda max. That's how you can predict it. And that's good gist of that. Okay, the next thing is then, this is an example from the book, Absorbance Spectra of Chlorophyll A and B. And this, again, is something you can do too. It's really good to extract the chlorophyll out of leaves. And you can do this with, I had a gal or a couple gals do this over the years where they would look at leaf senescence, the aging of leaves and how does that affect the chlorophyll content and how to use certain plant hormones to kind of reinvigorate the plant. And so you'd have to do this. You'd have to work it with leaves and pull the chlorophyll out, and then you just run this through, and you can get like the absorbance values of standards and look at the concentration of chlorophyll in your samples, and that can give you an idea of how much you've got there. So it's a real neat little experiment. So this shows you chlorophyll A and B have slight differences in their molecular structure. This difference results in different interactions with light. Therefore, they appear as different colors. And this is how concentration affects absorbance. If a sample has twice as many molecules as another, it can absorb twice as much light. This is true at any wavelength. It's important to know a sample's wavelength, the maximum light absorbance, so that the difference in absorbance due to concentration is obvious. And then that's it. So I'm going to stop this video right now for 7.1, and I'll move on to 7.2 in another video. Thank you.